Hello, my name is Agustín Martínez and I am a researcher in the Institute of Chemical Technology in Valencia. In this presentation, I will talk about the design of catalysts for the synthesis of valuable hydrocarbons through the catalytic hydrogenation of carbon dioxide in the context of the EU-funded eCOCO2 project. This is the outline of the presentation. First, I will briefly comment on CO2 emissions and its consequences and how catalysis might help in this respect. In particular, I will focus on the catalytic hydrogenation of CO2 as one of the most interesting technologies to transform CO2 captured from different sources into useful products. Then, I will briefly expose the approach proposed in the eCOCO2 project and its potential to improve the energetic and catalytic efficiencies of these technologies. Next, the different catalytic routes and catalysts that are under development for producing value-added fuels and chemicals from captured CO2 and green hydrogen will be introduced through several case examples from the literature and eCOCO2, and will finish with some general conclusions on this topic. It is needless to say that massive CO2 emissions from human activities, which are closely related to the uncontrolled use of fossil fuels, are mostly responsible of global warming and its consequences on climate change that we all are already experiencing in the form of more intense and frequent extreme weather events in different regions of the planet. The analysis of CO2 emissions by fuel type clearly indicates that the energy sector contributes by about 75% to the total emissions, and therefore its decarbonization is not only mandatory to fight the climate crisis, but urgent. In this context, catalysis becomes an essential tool to decarbonize the energy sector. Indeed, as shown in the slide, through the development of innovative catalysts and catalytic processes, catalysis would make it possible to replace fossil fuels by different alternative renewable and waste resources to produce a great variety of necessary products, including advanced fuels, commodity and specialty chemicals, and advanced materials with reduced carbon footprint. In particular, the utilization of CO2 captured from energy-intensive industries or directly from the air as a carbon feedstock for producing value-added products has proved to bring significant potential to mitigate carbon emissions. Among the available CO2 utilization technologies, its conversion to fuels and chemicals through catalytic hydrogenation using green hydrogen is especially appealing because it additionally provides an effective means to store and transport surplus electrical energy from intermittent renewable sources in the form of chemical energy. Most current CO2 to hydrocarbons conversion technologies rely on multi-step approaches involving several separation and catalytic processes that result in low overall energy efficiency and high cost. In contrast, the eCOCO2 project proposes a more energy and cost-efficient approach based on process intensification that enables the one-step conversion of CO2 to valuable hydrocarbons. Specifically, eCOCO2 makes use of an electrochemical ceramic membrane reactor powered by renewable electricity in which a multifunctional catalyst is integrated to realize the direct conversion of CO2 and steam into target hydrocarbon products. It is worth mentioning at this point that the electrochemical membrane reactor requires to be operated at minimum temperatures or 400 degrees Celsius. This limitation, as will be seen later, imposes some restrictions and challenges on the design of suitable catalysts for the eCOCO2 process. CO2 can be directly hydrogenated to different types of hydrocarbons that can be used as either liquid fuels or as raw materials for the petrochemical industry, such as lower olefins and aromatics. This process requires the use of multifunctional catalysts possessing different types of active sites capable of performing several catalytic steps in a single reactor via tandem catalysis. As it can be seen in the slide, the direct CO2 hydrogenation process can take place through two main catalytic routes depending on the nature of the reaction intermediates involved. Thus, in the so-called methanol-mediated route, CO2 is first hydrogenated to methanol that is subsequently converted into hydrocarbons according to known methanol to hydrocarbons or MTH reactions. In the other route, usually referred to as the Fischer-Tropsch route, CO2 and hydrogen react via the reverse water-gas shift reaction to form carbon monoxide as intermediate. Then, carbon monoxide is hydrogenated to produce hydrocarbons through the well-known Fischer-Tropsch synthesis reaction. The general aspects of the main catalytic systems that are being developed for each of these two routes and their special features in the particular context of the eCOCO2 project will be presented next. Regarding the methanol-mediated route, the most suitable catalytic systems, especially from the selectivity point of view, are those based on the oxide-zeolite or OX-CO concept introduced a few years ago by researchers at the Dalian Institute of Chemical Physics in China. The OX-CO catalysts comprise two geometrically separated catalytic sites provided by physical mixtures of a partially reducible metal oxide and a zeolite. Typical metal oxides include indium oxide zirconia, or zinc oxide zirconia, among others. The activation of CO2 and hydrogen and formation of the methanol intermediate occurs on surface oxygen vacancies of the oxide, while the conversion of the intermediate to hydrocarbons takes place on the acid sites of the zeolite. A particular feature of the OX-CO catalyst is the possibility to achieve high selectivity to a specific hydrocarbon fraction thanks to the fact that the conversion of the methanol intermediate takes place exclusively within the confined zeolite micropores of molecular dimensions. This slide shows some examples from literature for the direct CO2 hydrogenation to different types of hydrocarbons using catalysts based on the oxide-zeolite concept. For instance, at appropriate reaction conditions, the combination of an iron-doped zinc zirconium oxide and a medium-pore citizen-5 zeolite with low density of acid sites afforded nearly 60% selectivity to high-octane gasoline-range isoparaffins. In contrast, using SAPO34 having smaller pores instead of citizen-5 shifted the product distribution towards the formation of lower olefins in selectivities as high as 80%. Moreover, as shown in the right side graph, a high selectivity to aromatic type hydrocarbons of around 70% could be achieved for zinc aluminum oxide combined with citizen-5 having high density of acid sites. Nevertheless, these catalysts suffer from two main drawbacks that could compromise their potential industrial implementation. On one hand, CO2 conversions are generally low, typically below 20%, and on the other hand, the selectivity of carbon monoxide is most often too high, resulting in too low carbon efficiencies. This is particularly so when the catalysts operate at the high reaction temperatures required in the eCOCO2 project, as seen in the example of synthesis of lower olefins where the CO selectivity exceeded 60% at 400 degrees C. Therefore, increasing CO2 conversion and lowering CO selectivity are two of the main challenges in the design of more efficient oxide-zeolite catalyst. Due to these issues, in the eCOCO2 project, we mainly focused on developing iron-based catalysts operating through the Fischer-Tropsch route. Iron-based catalysts are active for both reverse water gas shift and Fischer-Tropsch synthesis reactions and can therefore produce hydrocarbons directly from CO2 and hydrogen mixtures in much higher conversion rates and carbon efficiencies than oxide-zeolite systems. However, the hydrocarbons produced on iron catalysts exhibit a broad carbon number distribution known as the Anderson-Schurz-Flory or ASF distribution that is innate to the Fischer-Tropsch chemistry and that limits the maximum attainable selectivity to a given hydrocarbon fraction. To overcome this limitation, iron-based catalysts were combined with zeolites to promote the in situ transformation of the primary Fischer-Tropsch products via acid catalysis and, in this way, to enable the formation of specific hydrocarbon fractions in selectivities well above those predicted by the ASF distribution. As an example, some of the results achieved in the eCOCO2 project using multifunctional iron zeolite catalysts are presented in this slide. In this particular case, we used an optimized iron catalyst promoted with an adequate amount of potassium and supported on an alumina with tailored porosity. The reactions were performed at temperatures compatible with the operation of the electrochemical membrane reactor, and at these conditions, all catalysts displayed high CO2 conversions above 50% with low CO selectivity of only 10%. As it can be seen in the bars graph on the left side, the hydrocarbons distribution was significantly affected by the zeolite pore structure. Hence, light olefins and liquid fuels were the main hydrocarbons formed on the large pore beta and modernar zeolites with a total selectivity of 70%. Differently, mainly liquid fuels and aromatics were produced over the citizen-5 zeolite comprising smaller pores. Besides pore structure, fine-tuning of other relevant properties is crucial to further improve the selectivity of desired hydrocarbons for a given zeolite. This is exemplified in the right side graph for catalysts based on iron and citizen-5, where the selectivity to aromatic hydrocarbons as well as to the most valuable BTX fraction could be increased from about 40 to 70% by adjusting the amount of Bronsted acid sites of the zeolite. Finally, the following general conclusions can be highlighted. The urgent decarbonization of the energy sector is mandatory to achieve climate neutrality. Catalysis is an essential tool to this purpose by enabling the efficient conversion of renewable carbon sources such as biomass wastes and CO2 into a wide range of value-added products. The direct hydrogenation of CO2 into different types of fuels and chemicals using green hydrogen and renewable electricity is one of the most interesting catalytic technologies for the valorization of CO2. This can be efficiently achieved using different types of catalysts following either methanol-mediated or Fischer-Tropsch catalytic routes. At the high reaction temperatures required in the eCOCO2 process, multifunctional catalysts operating through the Fischer-Tropsch route based on iron combined with an acid zeolite are the most suitable to produce valuable hydrocarbons at high conversion rates and high carbon efficiencies. Achieving high selectivity to a specific hydrocarbon fraction requires the fine-tuning of different zeolite properties. Thank you.